already discussed the work and the heat both are exchanged between the system and surrounding. When there is an inequality of temperature, heat will flow in between the two, in between the system of our interest and the surrounding around the system. Similarly, the work is also transferred between the system and surrounding when there occurs an unbalanced force between the two. In my last lecture, lecture number 2 in this series of chemical thermodynamics, I have explained the different type of works, its IUPAC convention of the sign of work, and also the magnitude to calculate magnitude of for the calculations of this work in a process. Among all these different works, mechanical work is very common in our chemical thermodynamics, and when the mechanical work is associated with this volume change of this gas, and we shall devote more time to explain the different type of mechanical works containing this gas, and the gas is enclosed in a cylinder fitted with a piston, and piston is frictionless, weightless and movable, means it is an idealized piston. And the magnitude of this mechanical work, I can write this mechanical work equal to minus integration V1 to V2 P external dV. P external dV. dV is the volume change of this gas present in this cylinder, and from V1 to V2, and the P external is the pressure applied by the surroundings on the piston of the system. And you can say this is the picture. Here a definite amount of this gas is contained within this cylinder, and here is the piston, and starting volume is V1, and at the start external pressure and internal pressure both are the same, and now we can increase this external pressure by adding the mass on this piston. If M is the mass added or placed over the piston, then the pressure is equal to mg by A equal to P external. M is the mass of this weight placed on the piston, G the acceleration due to gravity, and A area of cross section. Area of cross section of this piston. Whenever this external pressure is increased by placing these weights, the piston moves from V1 to V2, and it will move up to that limit until the P external equal to P internal. P internal is the pressure of this gas. Again, the system attains equilibrium. It is, and this equilibrium we call the mechanical equilibrium. And for compression of this gas, already I have discussed compressions of this gas, this dV, this dV is equal to negative, and so work is also this one is negative, P external positive, and here is negative, and multiplication of two negative terms is a positive, means work done on the gas by the surroundings, or on the system by the surroundings, and the system gains energy equal to the amount of work which has been transferred from the surrounding to this system. For the compression, for the compression of this gas, for the expansion of this gas, dV is positive, as V2 is greater than V1 in that case, and this W becomes negative, means work done by the gas, and whenever this is by this or by the system, whenever the system does work, its energy will lose, its energy will be decreased, and this is the magnitude of this mechanical work for the same volume change V1 to V2, from same volume change V1 to V2 depends on this external magnitude of the external pressures. Since the mechanical work is a path function, so this external pressure we can change, it may remain constant or it may also vary. If we do in one step, then the mechanical work we can calculate. If we do it in two steps or in multi steps or in a reversible process, this work, magnitude of this work will change depending on this process, though for the same volume change V1 to V2. And in case of a reversible process, actually this external pressure for the compression, external pressure is increased with an infinitesimal amount, and so volume will also change infinitesimal amount, and in that case this external pressure, the external pressure plus dP, external pressure, then external pressure becomes equal to P internal plus dP, but dP tends to 0 for this reversible process, so this P external then becomes P internal, means the pressure of this gas, and let it be denoted by P. P the pressure of this gas inside this cylinder. So reversible work in this case defined minus V1 integration V1 to V2 PdV. Now I show how the magnitude of this mechanical work depends on this path or way of this process by which the expansion, by which the volume change occurs from V1 to V2. If we do this expansion, if we do this volume change from V1 to V2 in one step, then suppose this is the gas and this is the P1 is the initial pressure, P2 is the final pressure, and P1 to P2 this pressure is changed in one step, and this is one step process, and the volume changes from V1 to V2. This is like that. Suppose here the 5 here the 5 kg weight have been placed on this piston, and then you are adding another 5 kg of this weight over this piston, and so this pressure is increased, volume will be decreased, and now this pressure over this piston is 5 kg plus 5 kg equal to 10 kg. And suppose this piston remaining in vacuum, so that no external atmospheric pressure or like that falls on this piston. Now this in one step process, this W1 equal to the P2 the external pressure. This volume change occurs against the constant external pressure. So the external pressure here, this external pressure is constant at P2, and so minus P2, and volume change, final volume minus initial volume, and graphically by means of indicator diagram I can show the amount of this work. Say V2 minus V1 means this is the V2 minus V1, or you can say if you remove this minus, then P2 into V1 minus V2. So this is V1 and this is V2. So V1 minus V2 is one side of this rectangular space, and this is P2. So this P2 and this one is the V2, V1 minus V2. This product of these two will give you this area. Area gives you this area. So whenever this same volume change V1 to V2 is done in two steps, suppose P1 to P2 dash, and then from P2 dash to P2. Suppose here there is our 5 kg weight already been given initially, and then you are adding this 3 kg in one step, and then the next volume change from V1 to V2 dash, and then again you are adding this 2 kg weight on this piston, then V2 to V2 dash to V2 is coming up the same volume change V1 to V2, but it occurs in two steps. The pressure is given. Suppose this is the 5 kg and this is 3 kg, and again it is 2 kg. Total becomes 10 kg. So P2 is equivalent to 10 kg, P1 is equivalent to 5 kg, but we are putting this weight in two steps. The amount of work required for this case minus P2 dash into V2 dash minus V1. V2 dash is the final volume, V1 is the initial volume, minus P2 dash is the constant, P dash is constant external pressure, and then it is minus P2 into V2 minus V2 dash. If we draw the diagram, then this is the area, work done or work required for this compression from V1 to V2 in one step. In this case, this is the area. This is the area, and area is found to be less, means the amount of work required to compress the same volume from V1 to V2, here it is found less than this one-step process. If we do it in multi-step process, suppose P1 equal to P internal plus dP. dP is very small amount of pressure is being added. Say at a time 100 milligram of weight is added. Initially it was this 5 kg, and then it is the 100 milligram, 0.1 gram is added at a time. So external pressure is increased, and this is internal plus dP, internal pressure is plus dP, and the volume change very small, say it is dV, the volume change occurs. And then successively this is P internal plus twice dP, another 100 milligram of weight is added on this piston, and this will be going on until this pressure volume changes from V1 to V2, and the pressure changes from P1 to P2, and dP is very small. So this is the multi-step process, and in each step the internal pressure and external pressure becomes equal, means mechanical equilibrium is attained in every step, and so this process the amount of work required to compress from V1 to V2 will be like that, P external into dV minus summation of all these steps, summation of this work required for all these steps, and so P external equal to P internal plus dP, and summation occurs, and this curve will be like that. And in this case the area is again less than it has become in case of one step or two steps. So we see that with the number of steps for the same volume change, if we increasing the external pressure very small amount, then the amount of work required is again smaller. If we consider the reversible process, means dP tends to 0, means suppose here 5 kg weight initially taken, which is equivalent to P1, and P1 and the internal pressure remains equilibrium, and then we are adding very small amount of this weight. Suppose we are adding some sand particles at one time. One sand particle is added, and then another sand particle is added, another sand particle is added, means this external pressure is changing by an infinitesimal amount. And so in this case it will go on like this until the pressure becomes P2 is the final pressure, and the volume changes from V1 to V2. Here dP tends to 0. So the amount of work required in a reversible process for compression from V1 to V2 equal to minus V1 to V2 integration Px. Now we can do this integration as the pressure and the volume both are changing continuously, and minus P external means P internal plus dP into dV, and since dP almost tends to 0, so P external equal to P external equal to P internal plus dP, P internal plus dP equal to P internal means the pressure of this gas, and we can write instead of pressure of this gas here P. So the formula for the calculations of this work done in a reversible process is minus V1 to V2 PdV. P is the pressure of this gas. And whenever we draw this graph, this multi-step process, it will start from here and it will go in this fashion, and here again least amount of work is required. This area will give you the least amount of work required to compress the gas, definite amount of gas from P1 to P2 in a reversible process. So this will be the area under this curve, and this will be the formula for the reversible work done. So the reversible work required to compress this gas from P1 to P2. Similarly, the work done by the gas for this expansion, whenever we shall consider the reversible expansion, for this reversible expansion of this gas, of a definite amount of this gas, this work reversible is equal to minus V1 to V2 into P dV, same formula. But dV here V2 is greater than V1, and so dV is positive and preceded by the P. dV is positive, P is positive, preceded by the negative sign. So this work becomes negative. Means in case of expansion, reversible expansion for a definite amount of this gas, the maximum amount of work is required. Maximum amount of work is done by the system. So suppose in this case it will be P external equal to P internal minus dP, and dP tends to 0. So in this case, this external pressure always kept maximum for the expansion of this gas. So in every step, this the external pressure is kept maximum. So overall, this total pressure in this reversal process will also keep this maximum work done by the gas. This is why we, if we like to get this maximum work, we always prefer the reversible work. So what we learn by this reversible process? In case of a reversible process, whenever the compression occurs, the minimum amount of work is required. Whenever the expansion occurs, the maximum work is done by the gas. And in this case, it is also shown that this the amount of this work done depends on this P external. And again, one thing is that whenever this reversible process is the infinite number of steps, or in case of reversible process, infinite number of steps will be required to do this either compression or expansion of this gas, and so this infinite time will also be required to complete this process, and this process is not a real one. You can say this process is a myth or the idealized process, and we like to see how much maximum work or the minimum work will be required if the process is done by this reversible way. Now I shall try to explain the work required for the compression in isothermal reversible process, adiabatic reversible process, and which one will be the greater, that I want to show you in the form of indicator diagram. Now I shall try to formulate the expressions of this work, mechanical work, for different processes. This formula could also be derived, but I have given all these formula required for these calculations as ready hand. And first I shall discuss this reversible process. Reversible isothermal process. Isothermal process means T of the gas is a fixed constant. And this for this formula this reversible equal to minus V1 to V2, and here P is the pressure of this gas, and this P is a function of temperature and volume and into dV. But whenever the temperature is fixed, then pressure is only dependent on this volume. And for ideal gas, so in that case, for ideal gas, this P equal to nRT by V. And so putting here, instead of P writing this nRT by V, we get work reversible in isothermal, or in short I can say reversible isothermal, and this is equal to nRT and integration minus V1 to V2 and dV by V. If we do the integration and put this limit, this one equal to minus nRT ln base E and ln V2 by V1. Whenever there is expansion, whenever there is compression, whenever for compression, V1 is greater than V2, V1 is greater than V2, and this one is negative, here it is negative. So this W reversible isothermal is equal to positive, means work done on the system. And for the expansion, of this gas, this V1 is less than V2, and WRI equal to this one becomes V1 is V2 is greater and negative sign, so this will be the negative work done by the gas, means energy would be released. And in this isothermal process, V2 by V1, we can write P1 by P2, which is the Waals law, at a constant T, and fixed amount of gas, So instead of writing this one, we can write work done in reversible isothermal is equal to this minus nRT and ln P1 by P2. If this temperature is not given in any problem, then instead of nRT, we can write P1 V1, or I can write P2 V2. In that case, this will be the minus P1 V1 ln P1 by P2, or equal to minus P2 V2 ln P1 by P2, or here it is minus P1 V1 ln V2 by V1, or this one equal to minus P2 V2 ln V2 by V1. These are the formula required for the calculations of this work done in a reversible isothermal process for this ideal gas. And when van der Waals gas have been taken, for the van der Waals gas, this and the process is isothermal, T is constant. In that case, this P equal to for van der Waals gas, P equal to nRT divided by V minus NV and minus AN square by V square. A and B, these two are the constants. A is coming from the intermolecular attraction and B is coming from the size effect. And whenever this P is replaced by this one, and it is called the linear integral, only one variable I can put here, and so this work reversible isothermal for van der Waals gas, it will be minus and integration V1 to V2, and here it is nRT divided by V minus NB minus AN square by V square and a dV bracket close. So this one, whenever integration is done and putting this limit, this one equal to minus nRT, T is constant and it is ln V2 minus NB divided by V1 minus NB, and in this case integration of minus 1 by V minus plus and again minus, so minus AN square into 1 by V2 minus 1 by V1. So, or if we take it a common minus, and then it will be plus. When A equal to B equal to 0, this form Ri becomes equal to minus nRT ln V2 by V1 and becomes equal to this form for ideal gas. And now I shall better it is written in this way, that will be good. Suppose this is the equations for the expressions of this. This is the expressions of this pressure in reversible isothermal for van der Waals gas. So we can write this equation is valid. Reversible isothermal van der Waals gas. This will be better. Now I try to find out the magnitude of this amount of work for this reversible adiabatic process. For this reversible adiabatic process, when the isothermal process is done, the system taken, all of these systems are taken the dithermal, so that the heat is good conducting between the system and surrounding. But whenever we are considering the adiabatic process, the system walls are adiabatic walls, or the walls of the system are wrapped by this good insulator, so that the heat cannot be exchanged between the system and surrounding. So in this case, if we try to formulate this equation, expressions for this work reversible is equal to minus integration V1 to V2 and here P into dV. P is the pressure of this gas for this reversible process. External pressure becomes equal to the internal pressure as the process occurs very slowly, and every step the external pressure and internal pressure becomes equal. Means every step, in every step the system attains the mechanical equilibrium. So it is the pressure of this gas. So for adiabatic process, this temperature is not constant, temperature must vary, and so for ideal gas in reversible adiabatic process, this relation is PV to the power gamma, so equal to constant, and gamma is the molar heat capacity ratio. So instead of say this is equal to K the constant, and this P could be replaced that P is equal to K divided by V to the power gamma. So this work done in reversible adiabatic process for this ideal gas, this minus, and this is V1 V2, and here K divided by V to the power gamma into dV, and we can do it minus K and integration V1 to V2 and V to the power minus gamma into dV. Gamma the molar heat capacity ratio. So again I can write minus K, and whenever this one is integrated and the limit are put here, then it will be minus gamma plus 1, and here this V2 to the power gamma minus gamma plus 1 and minus V1 to the power minus gamma plus 1 bracket close. And whenever this minus is common, then this one equal to this K divided by gamma minus 1 and K to be placed in between within this brackets, means K into V2 to the power minus gamma plus 1 and minus K into V1 to the power minus gamma plus 1, and this is bracket close. But K equal to P1 V1 to the power gamma equal to P2 V2 to the power gamma. So instead of write K would be replaced by this final state, and here K is replaced by this initial state, and whenever this one is done, gamma minus 1, and instead of K, P2 into V2 to the power gamma and into V2 to the power minus gamma plus 1 and minus P1 V1 to the power gamma and V1 to the power minus gamma plus 1 and bracket close. And whenever we are doing this one, 1 by gamma minus 1, and here it is only the P2 and V2 and minus P1 V1. Gamma is Cp by Cp, and this is the formula for reversible adiabatic process and ideal gas. This equation is valid. We can also write here in different form this one. What a reversible adiabatic, this one gamma minus 1 equal to Cp by Cv minus 1, and this one equal to Cp minus Cv by Cv, and this one equal to R by Cv for this ideal gas. So in the denominator this will be the R by Cv. And here P2 V2 is equal to N R T2. In the case of adiabatic process, there will be temperature change, and ANR T2 minus ANR T1 P1 V1. So if we take this common, ANR common, so and simplify this one, then this will be the ANCV T2 minus T1, and this is the again the work done in reversible adiabatic ideal gas. And now we can see, say for compression of this adiabatic compression of this gas, we know for this adiabatic compression there is a rise in temperature. Rise in temperature means T2 is greater than T1, and so W reversible adiabatic for this compression becomes positive. For expansion of this gas in reversible adiabatic process, whenever expansion occurs for this adiabatic process, there is a fall in temperature. So T2 is less than T1, and work reversible adiabatic equal to this negative. So these are the expressions. If we consider the Vander Waals gas, for Vander Waals gas, we have the first law, Q plus W equal to dQ. But for this adiabatic process, Q equal to 0, so W equal to dQ. And for this Vander Waals gas, this du, we can write this W reversible adiabatic for this Vander Waals gas equal to ANR NCV T2 minus T1, and minus AN square into 1 by V2 minus 1 by V1, and this is the reversible adiabatic and Vander Waals gas. This equation. Again, I can show for compression of the gas, of the Vander Waals gas, of this gas, for compression T2 is greater than T1. In the compression, temperature is increased and V2 is less than V1. So this one is the positive, but this one V2 is less, V1 is less, then 1 by V1, V1 is greater, then 1 by V1 less. So this term is also positive. Here V1 is greater than so V1 is greater, so this one is V1 is high, so this one is less, so this is minus. So what we see, in case of a Vander Waals gas, the amount of work done, magnitude of this work is less than it would be the ideal gas, as this is positive and this is negative. And means for compression, the less work is required to compress this gas as there is an intermolecular attraction. Easily the van der Waals gas is compressed. And for the expansion of the gas, that is a T2 is less than T1 and V2 is greater than V1. So in this case, this one is negative and this one is positive, means T1, this one is negative. So work done by the gas in case of compressions and more, and the less work is required. More work in case of expansion, there is a more work required to expand this gas against their intermolecular attraction. So what the net result for the compression, less amount of adiabatic work is required for this van der Waals gas. For the expansion, more work is required for the expansion of this gas. Compression less and expansion greater due to the intermolecular attraction. Now one thing I can say today, and this will be the last one, and I have discussed the two processes, one reversible two processes. One is a reversible isothermal process, and second one, this reversible adiabatic process. And I like to compare in which step, in which process the work done will be maximum. Here suppose we are considering the compression, suppose P here, and this is the initial state P1, V1, and both the gas in this case is compressed in isothermal fashion and in adiabatic process. And when this is the V1 and this one is the V2. V1 is greater than V2 in case of compression. We are considering the compression of the gas. Suppose ideal gas. So in case of this would be the isothermal curve, which is a rectangular hyperbola. This is the isothermal process, rectangular hyperbola, and it is the P2 and V2, the final pressure and volume. And for this adiabatic process, this one, here the P2 dash and V2, and we know this P2 dash is less than P2 for the same change of volume. This one is the adiabatic process. If we compare the adiabatic reversible isothermal work done and reversible adiabatic work done, if we compare, then the work done and reversible isothermal, when we are considering this isothermal, this is the area of this curve under this isothermal process, and for the adiabatic process, this is the curve. So from this indicator diagram, it is seen that the isothermal work done or the area under the head of this isothermal process is greater than work done in a reversible adiabatic process. Reversible process. This is quite obvious. In case of this isothermal process, heat is entered from the surrounding to the system and the system is doing work. But in case of this adiabatic process, this external, the surrounding does not or heat is not being entering from the surrounding to the system, and the system will do this work by its own cost of this internal energy. So this adiabatic work done in a reversible process must be the less than the work done in reversible isothermal process. This one is greater, this one is the less. So comparison is going on, could be shown very easily by means of this indicator diagram. Now the next class I will explain the irreversible processes and comparison of the reversible process, irreversible process, and the reversible cyclic process, irreversible cyclic process, and also I shall set some problems or examples to illustrate the subject matter. So thank you all who are watching this video. If you like, then please subscribe.